Position and momentum of quantum things are uncertain. But why? The simplest way to truly understand Heisenberg's uncertainty principle is not working through the math or listening to pop science statements. It's by looking at this visualization. So let's build this! Trying to understand Heisenberg's uncertainty principle, we often go through two stages. At first, we learn that this is Heisenberg's uncertainty principle. We cannot precisely measure a particle's position and momentum at the same time. In other words, you can't measure a definite number for position and momentum at the same time. One of them must be in a range of numbers. But this formulation has some problems. This leads to the common misconclusion that uncertainty is due to our abilities, that it's our fault that we can't measure precisely. You probably know that this is not true. It's not like we haven't figured out how to measure precisely, it's quantum mechanics that doesn't allow us to do any better. Which raises the question, why can't we measure precisely? Why is either momentum or position uncertain? What does it mean that quantum mechanics doesn't allow us to do any better? And this brings me to the second stage I went through when I learned about Heisenberg's uncertainty principle. At some point, I just came to accept that it is the way it is because that's what the math tells us. You can derive Heisenberg's uncertainty principle out of the math of quantum mechanics, and I'd say it's quite a pretty derivation. But just accepting that it is the way it is because of the math doesn't really help us to build an intuition. And while this technically answers the why question, why are momentum and position uncertain because of the math, this isn't really the answer we are looking for. So let's come up with a better answer. This is Heisenberg's uncertainty principle visualized. What you're seeing here are wave functions, so to understand this, we first need to talk about wave functions. But first, you can now hype my videos. This really helps support a small channel like mine, so thanks for your hype points and your likes. You probably know that in quantum mechanics, we describe particles with a wave function. The wave function describing a single particle contains all the information about that particle. If you have a wave function that describes multiple particles, it has all the information of all the particles. So, the wave function contains the information. The wave function does not correspond to a wave in the sense that it doesn't correspond to something going up and down. It doesn't correspond to an oscillating medium. First of all, the wave function is an abstract mathematical wave, but we can use it to calculate real things like position or momentum. And that's why we have to look at the wave function if we want to understand the uncertainty principle. The wave function's most important feature is that it tells us how likely it is that we will measure a particle at a certain place. The square of the absolute wave function is a probability distribution. So it's pretty likely that the particle is somewhere here, it's pretty unlikely that it's somewhere here, and it can never be here where the probability density is 0. But now you might say, how can a single axis describe the position of something? We live in a three-dimensional world, so we identify positions with 3 coordinates, not just with a single axis. And you're right. Actually, the wave function depends on all 3 space coordinates. This is just easier to draw. If we, for example, look at particles landing on a screen, this gives us the probability that a particle lands in this area. So here, the x-coordinate is the only coordinate we care about. Hence, it's the only one we draw. But back to the uncertainty principle. The shape of the probability distribution tells us something about the particle's position. Let's say the particle has a definite position, so it's exactly here and nowhere else. How does the probability distribution look? It looks like this. The probability to find the electron here is super high, because that's where it is, and hence the probability to find it somewhere else is 0. Actually, the uncertainty principle doesn't allow a super precise position like this. There must always be a little bit of uncertainty. So this is a more realistic shape of a probability distribution or wave function corresponding to a definite momentum. And this means the particle is most likely here, but it could also be here or here. So that's how the wave function tells us something about the uncertainty of the particle's position. What about the particle's momentum? The particle's momentum is directly related to the wavelength of the wave function. Let's say we have a wave like this, so we have a sine wave. Then this is the wave's wavelength. It's the same everywhere. So we have a definite wavelength and therefore a definite momentum. If we stretch or squeeze this wave, the value of the momentum or the wavelength changes, but it stays definite. The wavelength doesn't change. What about the particle's position? Well, if we square this wave, we get this probability distribution. It looks the same everywhere. Yes, there are some places where the probability is lower, but then there are also always places where it's higher again. And this stretches into infinity. So the particle could be anywhere. So the particle's position is really uncertain. Definite momentum means uncertain position. Let's go back to the wave function with definite position. What's going on with the momentum here? What's the wavelength here? How do you get the wavelength of a function which is not a sine wave? You have to construct it out of sine waves. And then the possible wavelength are all those wavelengths corresponding to the different sine waves. This means you get a range of possible different wavelengths and therefore momenta. To get a flat line, you can add all sorts of different waves, which means the wavelength can literally be anything. So the wavelength is not at all definite. It's as uncertain as it can be, and therefore the momentum is also as uncertain as it can be. The momentum can have every value: definite position, uncertain momentum. Those are the two most extreme examples regarding Heisenberg's uncertainty. In the middle you find something like this. Instead of a definite position, you have an area. And instead of a definite momentum or wavelength, you have a range of wavelengths. The shape of the wave function determines the definiteness of momentum and position. And if you make one more certain, you increase the uncertainty of the other one. This has nothing to do with our ability to measure, it's just how quantum mechanics works. So it seems like uncertainty is a fundamental property of our universe, at least according to quantum mechanics. Or actually, I should say at least according to some interpretations of quantum mechanics. Because what this means for our universe, what this actually tells us about our universe, that's up to debate. Do you have any thoughts on that? Please let me know. I must admit, I made a simplification I haven't told you yet. Technically, a wave function kinda has two parts. So instead of a single sine wave, the wave function would consist of two sine waves. But for understanding the uncertainty principle, this doesn't matter. However, if you want to know more about it, check out this video. Thanks for watching, have a wonderful day.